Okay, so moving forward to the last advanced technique. So we have the integration by partial fraction. So I think what you need here in this technique is that you need basic knowledge on partial fractions. So before, since we had advanced algebra course, so starting with algebra, then next semester we have advanced algebra. So we discussed partial fractions in advanced algebra course. So that's why when we came up with this, when we come across this topic in the integral calculus, so it's just a review for us since we have already tackled partial fractions in our previous courses. So for those of you who don't know partial fractions, so I think the aim of partial fractions is to transform your equations into a simple version of it. So it's partial fractions. So most likely, the aim is, let's say, from this term here, say that term, then it becomes a simple version, which is, let's say, a over something. So maragana siyang version. So it becomes a sa tawag na murag it's it it becomes its corresponding fraction parts. So if you multiply these two terms, so it becomes the original term as well. So the purpose of disintegrating your original equation is for us to be able to integrate easily, because if we try to integrate the whole term, so most likely we're going to have a difficult time integrating. Thus, we need to break it into its different partial fractions or component fractions so that we can easily integrate each term later. So I think that's the aim of the partial fractions. So we're going to have four different, so what we need to do here is we need to observe the factor in the denominator. So we need to observe this one. So if the form of the term in the denominator is ax plus b, so b being the constant term, so the corresponding partial fraction decomposition is ax plus b. So for example, you have multiple ax plus b in the denominator, so you're going to have plus b here. So b again, then ax plus b, then plus c, then ax plus b, so on and so forth, depending on how many terms you have in the denominator. So you're going to repeat this process because the first factor here is called distinct linear factor. So meaning distinct, so it's unique, it's different from the other factors that you have in the denominator. So distinct linear factor. So it's linear because it's raised to the power of 1. So examples of this one is x or x plus 1, or let's say x plus 3, as long as it's linear or raised to the power of 1. So you have a linear factor, distinct linear factor. Okay, so in the next line, so you have ax plus b raised to the power of n. So this one is still a linear factor, but it's raised to the power of n here. So instead of distinct linear factor, so we have a repeated linear factor. So what do you need to do here is you just have to use the formula from the previous line, and then you're going to repeat the process up until you reach the power of n. So for example, it's raised to the power of 7, so you have a over ax plus b, and then b all over ax plus b squared, then c all over ax plus b cubed, up until you reach the power of 7. Okay, so next is, as you can see here, you have ax squared plus bx plus c, and then this is the corresponding partial fraction decomposition. So you have ax plus b all over ax squared plus bx plus c. So this one is quadratic because it's raised to the power of 2, or the equation is of second degree. So distinct quadratic factor. So this one is distinct. And then the fourth line is repeated quadratic factor. Okay. So usually what we discuss in our advanced algebra course is that we go until the repeated quadratic factor. And since we know how to solve two or more unknown equations, or two or more unknown variables, so if you know matrix, so that's one way of solving five unknowns, six unknowns, or seven or more unknowns. So what we need to do here is we're going to solve for the unknowns here. So A, then let's say A, B, then A, B, and here A, B, C, and D. So we're going to have techniques on how to solve those unknowns. And also, I think most of the process that you're going to encounter here is integration by partial fractions first. So that's one of the most I mean, that's mostly likely the process of this integral equation or integral technique. So it's more on the partial fraction process and then less of the integral process. So I think it's 80% partial fraction decomposition, and then right after you got the corresponding partial fraction, and so that's the time that you integrate the equation. Okay, so you'll know that you'll know how to use the partial fractions once we go to the examples. So I think since you don't have any advanced algebra course before, or let's say most of you don't have partial fractions topic in senior high, so let's just try to solve up until distinct quadratic factor. Because usually in the departmental exam, this topic is a difficult problem because, again, since most of you don't have partial fractions during senior high, so that's why we lowered down a bit the difficulty of partial fractions, because you'll be solving um, two or more unknowns in the process. Okay, so let's try to solve three lang. So let's try to solve three problems, because the fourth problem is repeated quadratic, and you will be solving five unknowns in number four. So I think it's difficult for you to comprehend if you don't know how to solve five unknowns using matrix. So how do we know that we're going to use partial fractions? So first is you need to observe the equation. So how do you know that you need to use partial fractions? So the numerator must be of lesser degree than the denominator. So what do you mean by degree? So what do you mean by degree? It's the highest exponent being um, observed in the equation. Okay, so highest exponent of the variable, or highest degree of the variable. So in the numerator, so as you can see, the highest degree here is x to the power of 1 only. And then in the denominator, the highest degree here, or the exponent, is 2. Okay, so this one is first degree or linear against second degree, quadratic. So as you can see, the numerator is lesser degree than the denominator. So that's the time that you're going to use partial fraction. So for example, in number 2, so the degree in the numerator is third degree. So third degree. And the degree in the denominator, so this one is not third, so cube. Then you have x to the power of 1. So the degree in the denominator is fourth degree. Okay, okay. Excuse. So in number 3, so you have squared, so as the highest degree. So we didn't multiply squared then plus 1 here because it's already expanded. So unlike number 2, so since this one is still multiplication, so if you're going to expand the denominator in number 2, so the highest degree will be x to the power of 4. So that's why it's fourth degree. So here in the other example, so since it's already expanded, so the highest degree here is squared. Okay, so second degree. Then this one is third degree. Okay, so as you notice that every example is observed as the numerator being the lesser degree than the denominator. So same goes for number 4, so x cubed. And then again in the denominator, so since you still need to expand this one, so squared times squared will be fourth degree. Then you still have another one here, x to the power of 1. So this one is fifth degree. This one is third degree. So that's how you solve your, that's how you determine that you're going to use partial fractions. So of course, you also try to use u sub first if it's applicable, but I think if you are given these terms, so it's impossible to use u sub in the process since you have complicated terms in your numerator and in your denominator. So again, you can use partial fractions if the degree in the numerator is lesser than the degree in the denominator. So what if the degree of the numerator and the denominator is equal or greater than the denominator, di ba? So if it's greater or equal to, so you can use long division. So long division of algebraic terms. So for example, you're going to have x cubed plus 2x squared plus 1, plus x plus 1, then all over x minus 1. So the degree here is cube, and then the degree in the denominator is 1. So you can use long division. So x minus 1 divided by x cubed plus 2x squared plus x plus 1. Okay. So of course, again, if the degree is lesser than the denominator, so you're going to use partial fractions. Okay, so let's try to solve the first example so that you'll know so that you get the idea on how to solve partial fractions. Okay, so starting off with number 1. So what you need to do first is you need to observe the term in the denominator. So aside from observing the term in the denominator, so again, you need to observe if you're going to use a partial fraction. So since we know that the degree is lesser than the denominator, so you're going to use a partial fraction in the process. So next step is, since you know that you're going to use partial fraction, so the first step is you need to factor out the denominator. So factoring out is getting the factors of the quadratic equation. So this becomes x plus, so again, since the outer term is 6, so this must be 2, then the other one is 3. Okay, so this is the first step. So the first step is to factor out. All right. So next step is to determine what particular factors that you're going to have. So since you have x plus 2 and then x plus 3, so you're going to have distinct linear factors. So this one is one distinct linear factor. So I'm just going to make a abbreviation for this one. So this one is distinct linear factor, DLF. So x plus 3 is another distinct linear factor, DLF. So again, from formula is we're going to have a all over x plus 2. And then since we have another distinct linear factor, so next in the alphabet is b, and x plus 3. Okay, so the step number 2 is you need to identify the factors. Okay, so next step, this one is we're going to solve first the partial fraction before integrating your equation. So ignoring first the integral sign, so we ignore this one and apply this one later once we have reached the partial fraction decomposition. So you write first the equation on the left side. So this one is 2x plus 11. So all over x squared plus 5x plus 6. Then equals a all over x plus 2. Then plus b over x plus 3. So that's how you write your partial fraction. So again, the purpose of partial fraction is you're going to represent your original equation in terms of this format. So of course, once we have determined the values for your a and b, so upon addition, so it reverts back to the original equation. So the purpose of again the purpose of partial fractions is for you to determine its simple version. So the term before it was added up or it was grouped together. So that's the aim of your partial fraction. So let's write here. The third step is to solve the partial fraction. Solve the partial fractions. Or the third step is partial fraction decomposition. So you decompose the original equation into its fraction components. So next step is for us to eliminate the fraction so that we can have an easier view of the equation. So by doing this is we're going to multiply it with the LCD, or let's say multiplying it with the denominator on the left side of the equation. So that's x squared plus 5x plus 6. Or if you don't want to use this one, so use the factored out terms earlier so that you can have an easier view. So you can use this one here, the term earlier. So multiplied by x plus 2 and x plus 3. So if you expand this one, it's equal to x squared plus 5x plus 6. Okay, so since you multiply this one to the whole equation, so it cancels out the denominator. So this becomes 2x plus 11 is equal to a. So x plus 2 times x plus 2, x plus 3. So what remains is x plus 3 in the term, then plus b times x plus 2. So upon reaching this term here, so there are two methods in solving the unknowns a and b. So we're going to discuss both terms here, or both process. So we're going to do first elimination. So let's put it 3.1. So the first method is by elimination. So again, it's 3.1 because we're going to solve the unknowns a and b here, because we need it to transform the equation into this term here. So that's why we're going to look for the values of a and b. So the first one is by elimination. So in elimination, so you're going to let x be equal to something so that you can eliminate one term. So let's say if you want to eliminate a, or if you want to cancel out a, so let x be equal to, so if you want to cancel out a, so let x be equal to negative 3, so that negative 3 plus 3 is equal to 0. Or if you want to cancel out, if you want to cancel out a, x must be equal to negative 3. If you want to cancel out b, so x must be equal to negative 2, so that negative 2 plus 2 is equal to 0. Okay, so the elimination method is only best if you have two unknowns. So that's why I'm going to show you two methods on how to solve the unknowns here, because in the next examples, so you'll be solving more than two unknowns na. And I think the best method for that one is the second method that I'm going to show you, which is equating coefficients. So let's try to solve first by elimination. So again, if you want to eliminate one variable, let's say a or b, so you're going to let x be equal to something. So let's say we're going to eliminate b first. So at x is equal to negative 2, diba? So if this one is negative 2, so you're going to cancel out b. So of course, if you let x be equal to something, so it applies to all x variables in the equation. So this becomes 2 times negative 2 plus 11 is equal to a times negative 2 plus 3 plus b times negative 2 plus 2. So notice that negative 2 plus 2 is 0, so it cancels out the b parameter. So what's left in the equation is you have negative 4 plus 11 is equal to a times 1. Okay, so your a term here is 7 is equal to a, or a is equal to 7. Alright, so since we have determined a, so we need to eliminate a in the next step by letting x be equal to something. So at x is equal to negative 3 this time, because we need to eliminate a variable now. So this becomes 2 times negative 3 plus 11 is equal to a times negative 3 plus 3 plus b times negative 3 plus 2. Okay, so again, this becomes 0 because negative 3 plus 3 is 0. Then 0 times a is 0. So you have negative 6 plus 11 is equal to b times negative 1. So you have 5 is equal to negative b. So b is equal to negative 5. Okay. So your equation. So again, if you're going to write your equation now, so your equation from this term here, so it becomes the integral of 7 over x plus 2 minus 5 all over x plus 3 dx. So again, notice that from the original equation, so the equation becomes its corresponding partial fraction decomposition, which is 7 over x plus 2 minus 5 over x plus 3. So that's the first method. So do you have questions so far for the first technique? Okay, so no questions. Okay, so let's try to solve using the other method, which is sorry. Okay, so sorry. Um, so let's try to solve it using the other method, which is by equating coefficients. So let's try to use another color so that we can distinguish the two methods. So 3.2 now. So by equating coefficients. Okay, so let's copy the equation. So I think it's 2x plus 11 is equal to a times x plus 3 plus b times x plus 2. Okay, so in equating coefficients, so since we're going to equate coefficients, so the process here is we need to expand this term here. So I think this one is a bit complicated, or it's a longer process compared to the elimination method, but the advantage of equating coefficients is that you can solve two or more unknowns here. So two or more unknowns. So that's the advantage of equating coefficients against the elimination method. So elimination method is it's only best if you have two unknowns, but if you have more than two unknowns, so the best method to determine your unknowns is by equating coefficients. So what you need to do here is you need to expand the term above. So expanding and also expanding this one. So you have ax plus 3a plus bx plus 2b. So let's try to verify if we have the same. So 2x plus 11. Okay. Okay, so after expanding is we're going to group together your equations because we need to equate the coefficient of x here against the coefficients of x on the right side of the equation. So constants on the left side also with the constants on the right side of the equation. So we're going to group the x's first. So ax plus bx, and then group together the constants. So that's 3a plus 2b. Okay, so since we're going to equate coefficients, so we must factor out the x parameter. So a plus b times x plus 3a plus 2b, which are constants. So again, since the process is called equating coefficients, so we're going to equate the coefficient of x on the left side with the coefficient of x on the right side. We're going to equate the constants on the left side of the equation against the constants on the right side of the equation. So the proper method or the proper way to do this is for you to be not confused. So starting off with the x parameter, so x and then semicolon, so that you know that you're going to equate coefficients of the x variable. So 2 on the left side is equal to a plus b. Okay, and then next is the constants, so c. So that's 11 on the left side, and then the right side is 3a plus 2b. So it's valid because in algebra, if you have two unknowns, you need two equations to be able to solve the unknown parameters. Okay, so since you now have two equations, so you can either use your elimination method or you want to use your substitution method in solving for a and b. So for me, the easiest method for this one is for me to use elimination. So I'm going to eliminate, let's say, b first. So I'm going to multiply negative 2 to the entire equation. So this becomes negative 4. This becomes negative 2a. This becomes negative 2b. So upon addition, so negative 4 plus 11 is equal to 7. Negative 2a plus 3a is a. Then negative 2b plus 2b is 0. So the first term is a is equal to 7. So you can either use equation 1 or equation 2 to solve the other unknown parameter. So since equation 1 is most likely the easier term because you don't have to multiply the variables, so that unlike equation 2, so you have 3a plus 2b. So let's use equation 1. So using equation 1, so that's 2 is equal to 7 plus b. So 2 minus 5 is equal to b. 2 minus 7, I mean. So that will be negative 5 is equal to b. So b is equal to negative 5. So I think that's the same answer as earlier. So those are the two techniques on how to solve partial fractions. So it's either by elimination or by equating coefficients. So again, equating coefficients is advantageous if you have two or more unknown parameters. So if you have only two unknowns, so it's best to use elimination. Okay, so let's try to solve the integral now. So the equation becomes, again, as what I have written in the previous slide. So this is 7 all over x plus 2 minus 5 all over x plus 3 and then dx. So again, since we're going to manually solve this one each term because dx will be distributed to the two terms here. So if you know the shortcut or if you have solved many equations by now, so you know that the integral for these two terms is ln. But if you don't want to be so if you don't want to be unsure with your answer, so of course let's try to individually get the answer for this one. So let u be equal to x plus 2. So derivative of u is equal to dx. Okay, so same goes for the other term here. So x plus 3, then du is still dx. So the two terms here becomes the integral of 7, 7 integral of du over u. Then the other term here is minus 5 integral of du over u. Okay, so the answer for this one is 7 ln because we have the integral of d over u is ln. So x plus 2, then minus 5 ln x plus 3 plus c. So this is the final answer. Okay. So questions so far or clarifications? So muna siya. Okay. So muna siya. So again, so the steps are super clear. So 1, 2, 3, and then 3.1 or 3.2 depending on the unknowns that you're going to have. And then the fourth step is to integrate. So fourth step is to integrate. So notice that 80% of the process is purely from partial fractions. And then the integration process is just a few lines in the process of getting the final answer. Okay, so let's move on to the next example. So this time is we have the integral of x cubed minus 1 all over x times x plus 1 cube. So again, the first step is for you to factor out the denominator. So since this one is already factored out, so this one is x plus 1 cube. So notice that your denominator is already factored out, so it's not expanded. So second step is for you to determine the different factors. So the first term here is a distinct linear factor. So this gives us x, this gives us a all over x. So a all over x. So the next term is a repeated linear factor because it's raised to the power of 3. So this one is repeated linear factor. So this gives us b. So since we now have b here, so starting with the first term, x plus 1, going to the x plus 1 nth power. So next is c all over x plus 1 squared, then plus t x plus 1 cube. Okay, so next step is for us to determine the partial fractions. So again, writing the original equation on the left side. So x cubed minus 1 all over x times x plus 1 cube. Okay, so it's equal to a all over x plus b all over x plus 1 plus c all over x plus 1 squared plus d all over x plus 1 cube. So notice that we're going to solve 4 unknowns now instead of 2. So eliminating the fractions by multiplying it with the LCD. So that's x times x plus 1 cube. So the equation becomes x cubed minus 1 is equal to, so a, so since the denominator is x, so what's left is x plus 1 cube and plus b. So that will be times x plus 1 squared, then plus c, and times x plus 1, and then plus d times x. Okay, so again, since elimination method is only limited to two unknowns, so we're going to solve this one using equating coefficients. So again, if you're going to try using elimination here, so it's difficult to solve all the variables a, b, and a, b, c, and d. So again, using equating coefficients, so let's just try to put here 3.1. So by equating coefficients. So again, we need to expand the term above. So this becomes x cubed minus 1 is equal to a. So the expansion of x plus 1 cube. So from algebra, since this one is perfect cube, so this one is x cubed plus 3x squared plus 3x plus 1. So that's a shortcut. Then next is you have b times x squared plus 2x plus 1. Then plus c times x squared plus x. Then lastly is just dx. So expanding it further, so you now have ax cubed plus 3ax squared plus 3ax plus a, then plus bx cubed plus 2bx squared plus bx plus cx squared plus cx plus dx. Okay, so we're going to group together cube, squared, x, and the constants. So starting off with the cube terms, so cube ax cube bx cube. So in shortcut, so this becomes a plus b times x cube. Okay, so just be very careful with the operation sign. So in some equations, you're going to encounter minus or plus. So just try to be careful with the signages or the signs of operation in grouping together your terms. So next is your squared terms. So 3a squared, 2bx squared, cx squared. So this becomes 3a plus 2b plus c times x squared. So next are your x terms. So 3ax, bx, cx, and then dx. So plus 3a plus b plus c plus d times x. Then the only term remaining is your constant, which is just a. Okay, so we now equate coefficients. So let's try to write it on the upper right of this page. So starting with x cubed, so x cubed on the left side. So the coefficient of x cubed on the left side is just 1. So equal to a plus b. So next is x squared. So the coefficient of x squared on the left side. So since there's no x squared term here, so again on the left side. So since there's no x squared term on the left side, so this one is 0. Then the right side, if we have since we have an x squared term on the right side, so that's 3a plus 2b plus c. So you get the idea, right? You need to equate the coefficients. So coefficients of the variables. So coefficient of x on the left side. So upon observation, so since there's no x on the left side, so 0. Then the right side is since we have coefficients of x variable, so that's 3a plus b plus c plus d. And then lastly is your constant. So on the left side, that's negative 1. Then the right side is only one constant, which is a. So we have 4 equations to solve. So again, since you have 4 unknowns, so you need 4 equations. So it's valid because we have 4 equations created. Okay. So looking at your equations, so upon looking at equation number 4, so a is automatically negative 1. So upon observation also, so you can just use substitution to solve for the other terms. So let's say using equation 1 to solve for b. So you have 1 is equal to negative 1 plus b. So b is equal to 2. So next is using equation 3 to solve for c. So you have 0 is equal to 3 times negative 1 plus 2 times 2 plus c. So negative 3 plus 4. So that's 1. Then transpose to the other side. So c is equal to negative 1. Then lastly is using equation 3 to solve for the d parameter. So 0 is equal to 3 times negative 1 plus 2 plus negative 1 plus d. So d is equal to 2. Okay. So since we have solved our equation, our partial fraction decomposition, so we can now integrate. So let's integrate it on the next slide. So going back to the red color, so again the fourth step is for you to integrate. So the equation becomes, so the first one is negative 1. So negative 1 over x. Then next one is plus 2 all over x plus 1. And then c is negative 1. So let's try to verify. So c is negative 1, then d is 2. So negative 1 all over x plus 1 squared, then plus 2 x plus 1 cube dx. Okay, so upon integration, so you're going to integrate the individual terms inside the parentheses because you need to distribute dx. So again, if you want to solve them individually, so starting off with the first term, that's 1 over x. So this one is purely ln x. So again, if you want to verify that it's ln x, so let u be equal to x, then du is equal to dx. So this term here becomes negative integral of du all over u. So for the second term, is you're going to have u is equal to x plus 1. Then du is still dx. So that's 2 integral of du all over u. Okay, so for the third and fourth term, so since this one is raised to any power, so squared and third degree, so the same u sub technique, but the equation becomes negative integral of du all over u squared. Or if you want to express this in the numerator, so this becomes negative u to the power of negative 2 du. So it's not ln, di ba? So it's not always ln answer for your partial fractions. So in the last term, this one becomes plus 2 integral of du all over u cube. So in the numerator expression, so this one is 2 integral of u to the power of negative 3 du. So again, if we try to integrate each term here, so this becomes negative ln u, which is negative ln x. So the next term here is 2 ln u. So this one is 2 ln x plus 1. So the next term here is so negative. Then again, basic formula, plus 1 all over n plus 1. Okay. So this becomes so negative, negative. So this becomes plus u to the power of negative 1 over 1. Or you have, so in easier terms, so this one is 1 over u. So 1 over u. Or this one is 1 all over x plus 1. So let's try to erase lang para we have space. So again, negative times negative. So this one is 1 all over u. So positive. And then it becomes 1 over x plus 1. So the other term here is 2 times u to the power of negative 2 all over negative 2. So 2 and 2 cancels out. Then you have negative 1 all over u squared. So that's negative 1 all over x plus 1 squared. So grouping together your answers, so the final answer is negative ln x plus 2 ln x plus 1. So third term is plus, so 1 all over x plus 1. Then the last term is negative, so minus 1 all over x plus 1 squared plus c. Okay, so that's the final answer for number 2. So notice that notice that it only gets longer if you're going to have to solve more unknowns in your partial fraction. Okay, so questions or clarifications regarding the example. So again, this one is the process. So the process of determining the unknowns for your partial fraction decomposition. And then on the right side is this one is the integral process. So I think you can just review this one in the recording since what I have presented is of different colors. So per step, I'm going to use different colors sa mga methods. So in factoring out and determining the factor, so I used green, and then getting the expression for the partial fraction decomposition. So that's blue. And then the purple one is the method for determining the unknowns of the partial fraction decomposition. So it may be by elimination or by equating coefficients. So I think there's also the number. So 1, 2, 3, then 3.1, and then 4. Okay, so I think there's no question. So let's proceed to the last example. Excuse. Okay, so sorry. Okay, so moving to the last example. So again, step-by-step process. So need to factor out the denominator first. So don't forget also that the first method is always to try to determine if you're going to use partial fraction. Okay, so that's the first step. But if you know that you're going to use the partial fraction, so of course the first step in determining your partial fraction is to factor out the denominator. So factor out the denominator. So looking at your equation in the denominator, so x cubed plus 2x squared plus 5x. So we can factor out x, then times x squared plus 2x plus 5. So notice that your x squared plus 2x plus 5 cannot be factored out further since the middle term is 2x and the constant must be 1 for it to be factored out completely. So since we cannot factor out anymore, so the next step is to determine the different factors. So the first one is a distinct linear factor. So this gives us a all over x. And then the second one is a quadratic function or quadratic factor. So since it's distinct, it's not repeating. So this one is distinct quadratic factor. So again, from the formula being presented in the first slide, so this one is bx plus c. So bx plus c all over x squared plus 2x plus 5. Okay, so next step is you're going to solve your partial fraction. So writing the equation first, the original equation. So x squared plus 4x plus 10 all over x cubed plus 2x squared plus 5x is equal to, so the partial fraction decomposition being determined in the second step. So ax plus bx plus c all over x squared plus 2x plus 5. Okay, so next is we eliminate the fraction so that we can have one line of equation. So multiplying with the LCD or the factored term in number 1. So that's still the same. That's the LCD also. So x times x squared plus 2x plus 5. So our equation becomes x squared plus 4x plus 10. So again, the denominator is eliminated because if you try to expand this one, this also gives us x cubed plus 2x squared plus 5x. So the purpose of using the factored out terms is that it's easy for us to determine which terms are to be multiplied with your unknown parameters. So a times the quadratic factor, and then plus bx plus c times x. So again, since we have three unknowns, so it's best to use equating coefficients. So 3.1, so by equating coefficients. Okay, so we need to expand the term above, so this one. So this gives us x squared plus 4x plus 10 is equal to ax squared plus 2ax plus 5a, then plus bx squared plus cx. So again, we have x squared term for x and then 10. So we need to group together x squared first, and then the x variables, and then the constant terms. So grouping together the x squared terms first, so ax squared, bx squared. So this one is a plus b times x squared. So shortcut lang. So I just group them together immediately. Or I just factored out x squared in the process. So next is the x term. So 2ax and then cx. So plus 2a plus c times x. And then the last term here is 5a. So 5a being the constant. Okay, so we now equate your coefficients. So starting off with x squared. So x squared semicolon. So the coefficient of x squared on the left side is 1. Then the right side is a plus b. So next is x term. So the coefficient of x on the left side is 4. Then the right side is 2a plus c. Then lastly is your constant. So that's 10 on the left side, and then 5a on the right side. So you have three equations, three unknowns. So upon observation, we can solve a. So using equation 3, so we can solve a. So that's 10 is equal to 5a. So a is equal to 2. And then you can you can use equation 1 to solve for b, and equation 2 to solve for c. So 1 is equal to a plus b. So 1 equals 2 plus b. So b is equal to negative 1. And then lastly is your equation 2. So that's 4 is equal to 2a plus c. Then 4 equals 2 times 2, and then plus c. So c is equal to 0. All right. So we are done with the partial fraction decomposition. So next step for us is to integrate. So we now have the integral of, so the first unknown is 2. So 2 all over x, and then plus, so that's bx plus 0. So negative 1 times x plus 0 all over x squared plus 2x plus 5. dx. So the equation becomes the integral of 2x minus x all over x squared plus 2x plus 5, and then dx. Okay, so we now integrate individually. So for the first term, so I think it's super easy. So let u be equal to x, and then du is equal to dx. So this gives us 2 integral of du all over u, which gives us 2 ln of u, or 2 ln of x. So we have solved the first term already. So for the second term, so I think this one is a complicated equation. So kani siya super libog man siya nga equation. So my tip here is you can try to get the complete square of x squared plus 2x. So by doing that is we're going to have x all over x squared plus 2x plus 1. Diba? The perfect square. And then plus 4. Because 1 plus 4, so if we try to expand this one, it leads us back to the original equation. So the purpose of this one, so why do we need to do this in this manner? So that we can use u sub later. So again, we can determine this particular process through constant practice of integrating equations. So if you can solve many equations, so you can know that you're going to do this particular technique. Okay, so this becomes x all over x plus 1 squared plus 4. Okay. So this time is we're going to use u sub. So u is equal to x plus 1. Then du is equal to dx. So notice that there's a x variable above the equation. So in terms of x, so this becomes u minus 1 is equal to x. So the equation becomes u minus 1 in the numerator. So all over u squared plus 4 and then du. Okay, so since we have two terms in the numerator, so we can separate it. So we can separate them we can separate them into two terms. So what they mean by this is we can have u all over u squared plus 4, okay, minus 1 all over u squared plus 4. Diba? So notice that we can do this basic concept here. So let's try to write it again on this side. So we have the integral of u all over u squared plus 4, then minus 1 all over u squared plus 4. Okay. So in the first term, so we can try to integrate this one using another u sub. So since we're going to use another u sub and our variables are now in u, so let's try to use z. So z is equal to, so let's say u squared, this one is du. So let's try to use z. So z equals u squared plus 4. So derivative for this one is dz is equal to 2u du. So notice that the numerator has a u du here, u du, diba? So isolating um, u du, so you have dz over 2 is equal to u du. Okay, so the integral of the first term becomes the integral of, so starting off with u du, that's dz over 2 all over z. Okay, so the integral for this one is, so this becomes, so this becomes the integral of 1/2 ln z. Okay, so bringing back the value of your z term here, so you have 1/2 ln u squared plus 4. Then upon bringing back the value of u, so the exact answer for the first this term here is 1/2 ln x squared plus 2x plus 5. So I just expanded immediately because u squared is x plus 1 squared. And upon expanding, so it leads me back to x squared plus 2x plus 5. Okay, so the last term to be solved is this one here. So notice that this one is inverse trigonometric function format. So 1 over u squared plus a squared. So this one gives us the arctangent. So u squared is u squared, u is u, and then a squared is 4, a is equal to 2. So the answer for this one is negative 1 over a arctangent u over a. So that's negative 1/2 arctangent. So our u is still u, okay, over 2. So bringing back the value of your u parameter, so coming from this term here, our u is x plus 1. So that's 1/2, negative 1/2 arctangent x plus 1 all over 2. Okay, so final answer. So don't forget that this one is minus because this one is coming from here, minus, then minus, 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 minus. Okay, so the final answer is, so let's go back to the red one. So final answer is 2 ln x. So again, minus the integral of the first term. So that's minus 1/2 ln of x squared plus 2x plus 5. Okay, and then minus times minus, that's plus. So plus 1/2 arctangent x plus 1 over 2 plus c. So this is the final answer. Okay, so questions or clarifications? So I think, okay, so I think what will appear in the exam are just simple partial fractions. So I don't think you're going to reach quadratic factors. So if you're going to reach quadratic factors, so it may be just a simple quadratic factor. So you won't be solving number 4 because since we're going to solve 5 unknowns and again you don't know how to use matrix, so I think it's difficult for you to solve 5 unknowns. Okay, so since there's no question, So I think we can meet again on Friday so that we can discuss the final topic, which is your definite integral.